Welcome back to 3D CAC Home Edition, everyone. I'm Kate Hubbard with Action Engineering, and this week we're revisiting the door hinge from last month's CAD Hackathon. We had so much to talk about in the last live session that we didn't get around to demonstrating GD&T Advisor as promised. So we released that demonstration of the GD&T principles in preparation for this event today, and we'll replay that 6-minute clip to get us started. And to introduce you to our experts, we've got Stephen Werst joining in from Sigmetrix. Stephen's the Director of Customer Success and Product Strategy and our GD&T Advisor guru for today's Q&A. And joining Stephen is Ryan Gelotte, Action Engineering's Chief Technology Officer and our unofficial professor of MBD. And this session is really about all of you in the audience. Ryan and Stephen are here to answer those burning GD&T or MBD questions. So while we're reviewing that short clip, go ahead and begin adding your questions for the experts in the Zoom chat, and we'll get to answering those right after it's finished.
So last time we talked about the Hinge and went through the GD&T and had some good discussion about it. Here we're going to have open the Hinge here in Creo. So we have the one Hinge half open in Creo and demonstrate how GD&T Advisor, which is a Sigmetrix product, can guide you through proper application of GD&T. Functional GD&T at that. First, the model had to be sort of tweaked to convert that whole into 2 surface regions. And now you'll see we're starting with picking a feature to be our primary datum feature. It's a planar surface. Pick that bottom surface. It recognized it as a planar surface and actually recommended to use flatness to qualify that. And there was a little checkbox that automatically identified that as datum feature A. Next, if we move on to datum feature B, right, we split that whole into 2 surface regions and collected that. And then the reason we split that into 2 regions was so that we could add, in what you'll see here in a second, the continuous feature modifier. So that is a feature of size. Here we're going to add that continuous feature modifier as well as the true position tolerance to qualify that. And there you see now we have datum feature B qualified as a feature of size along with its true position tolerance. And you can see there it added the datum feature symbol as well to that. And again, it actually recommended true position as the optimal tolerance type to qualify this datum feature. And here you can see we had the flexibility to change the placement of that datum feature symbol to hang off the bottom of the feature control frame. Lastly here, we're going to define the width of that slot you see there in between the 2 holes as datum feature C. Right, that's going to be a feature of size, the width of a slot. It recognized that feature as a slot. It's also recommending to use perpendicularity as the geometric tolerance feature to qualify it, right? And then it automatically created our size dimension as well as the perpendicularity tolerance and gave us the option to identify that as datum feature C all in one workflow there. Next, we're going to go then and continue to tolerance the rest of the model. So here we picked that flat face as well as those 2 fillets. It recommended a surface profile tolerance, and we just completed the rest of it. We wanted that to be a surface profile of 0.5 back to datum features A, B, and C, using a max material boundary modifier for datum feature C. Right, and here you can actually see we're updating that datum reference frame, right? It by default applied the MMB modifier to that. We didn't want that, so we had to go back and edit the definition of that datum reference frame to remove that. Notice it automatically updated any geometric tolerances that were using that datum reference frame. So now we're doing the extrude feature there. Same thing, we're picking the geometry. It recognized that as a feature and recommended surface profile, as well as reusing that same datum reference frame. We're doing the same thing here with the holes, right? And that's actually a pattern. So we are able to select all 3 of those holes, and it's going to recognize that as a pattern of holes. And then it'll also recommend which geometric tolerances to use to qualify those holes. And then we can complete the definition by providing a true position value. Well, actually, first here we're applying a size tolerance for the size of the hole. And then we can further define this with our true position. So we have our size tolerance as well as our positional tolerance. So now that feature's fully constrained in both location, size, form, and orientation. Now we'll move on to the chamfers. And again, there's 3 of those. So pick those features. It recognizes that as a pattern. It recommends a surface profile tolerance type. We just give it a tolerance value, and there we have those 3 surfaces with a tolerance of 0.02 applied back to that same datum reference frame, A, B, and C. Next, we will tolerance the top of this hinge plate. So it recognized that as a planar surface feature. There again, it's recommending a surface profile tolerance to be used here. And that one, actually, we're just going to the datum reference frame of A, because we're really only interested in its relationship to datum feature A, which is really going to control the thickness of that plate. So that we don't have to have a consumer query the model to find out what that thickness is, we're going to go ahead and add a basic dimension here to give you that information. So while that's being finished, I just want to summarize, right? GD&T Advisor was able to be used to select the features that the desire was to establish them as datum features, provided some advice, hence the GD&T Advisor name, of how to qualify those features. As the datum features were qualified, it was just creating those datum reference frames that could be used for other geometric tolerances. And then the same workflow approaches, you could select the features and it would add the necessary geometric tolerances as well as any size dimensions necessary to fully define those features. Thank you, and I hope you enjoyed the demo. So, we're really going to lead into the Q&A session. We do have a couple questions that were already submitted that we'll start with. Got Rick Kerner already adding another question, but I want to just start real quick with one of the questions that Angel Lovey, I hope I pronounced your last name correctly, posed when we did part 1. It was during that same day, and it wasn't specific to the hinge plate or the hinge that we were just looking at, but it was to the pin. And it was a good question because the pin has a primary datum feature of really just the main shaft of that pin, and we used a tolerance of plus or minus 0.02 over a length of a pin that was about 2.5 inches long. And Angel brought up a good point. You know, wouldn't you want to qualify that? That's a pretty tight tolerance for a for such a long feature using the envelope principle. It doesn't really allow for that cylinder, you know, to be held with a 0.02 plus or minus 0.02 tolerance over such a long length. So could we add a straightness tolerance to further refine that, you know, and allow for that pin to, you know, allow some bent form there. So Stephen and I had a pretty good discussion after our part 1 about that, and looked at things. You know, does that pin? You know, you have to kind of go back to the requirements. Is that pin allowed to be inserted with a hammer? You know, so you know, is there an allowable amount of deflection there that would be overcome by inserting the pin into the hinge? You know, we got into some of those types of discussions, and really what we arrived at was that the first session we focused on defining the relationships between features. And I'll concede, I took my best guess at the values of the tolerances. And what became apparent was that I don't have that experience of designing hinges, right? And as a designer, I don't necessarily like to do the math. So, the workflow kind of presented in part one was defining the relationships. I can't say that I had a level of confidence that the tolerance values I established were right. I came from a background where we designed very intricate electronics. So those are the types of tolerances that I was used to dealing with. I like to define the relationships and let the software do the math, such as like CE tall. So that was kind of where that discussion led. Stephen, do you have anything to add to that?
No, I think you covered it well. I mean, just to reiterate, I think it was a slight difference in the fundamental assumptions of what we, if we're assuming the pin's just going to easily slip through the three holes, then really kind of that outer boundary is important, and whether that's consumed through size variation or form error, straightness error, is somewhat irrelevant. However, if it's important to get a specific fit into one of those diameters so that you don't have to get the big hammer out to make it fit, then obviously you want to kind of separate that and say the size has to be within this range, but we can also allow it for some additional deformation so that it can be manufactured. So it was a good question that sparking to a good exchange back and forth. There was actually a question that just showed up in the chat just to help everyone understand, make sure that everyone's on the same page of what we're talking about. Ryan, you mentioned the term qualify a datum. And basically what we're talking about here is making sure that the characteristics of that feature are defined as needed. So with a primary datum, typically it's the form. And if you're dealing with a secondary, you qualify it with an orientation or perhaps position, depending upon how it relates to the primary. Just making sure that everything is specified for that feature that needs to be. So when the term qualifying the datum just means making sure that the appropriate tolerances have been applied to the datum.
Yeah, I just saw another question. Rick Kerner put one in. Wouldn't one want a composite GD&T for the whole pattern? I'm not sure. Composite true positions are going to refine orientation. So I really don't think there's a need for a composite positional tolerance for the whole pattern in this case. Especially over such a small thickness that hole's got to go through. I think a single frame single line feature control frame true position is sufficient here. Does anybody have any other, response to that?
There were two different ones, I think.
Oh yeah.
You're addressing Rick's with the composite call out, and then there was another one about why not combining the hole and the countersink into a single call out.
Right. Yeah. So my response was in response to Rick's about the composite. Don, yours question is a valid one. There is whole notes are a challenge. You could, when you look at a whole note where it has a drill diameter plus a countersink symbol, there's multiple characteristics embedded in those whole notes. I kind of see where you're going with that. Unfortunately, in the Creo world, and actually all the CAD applications, those whole notes haven't really caught up to the semantic definition of holes. Where you're really trying to call out, two or more characteristics in one note. Can't say I disagree with your comment, but as far as the hole and the countersink drift in different directions, that's again where I would look at a tolerance analysis solution to tell me what is allowable there. Stephen, did you have anything to add to that?
I don't want to open up a can of worms here. I think part of it too, when we were looking at this and discussing it on the recommended approach, we chose profile because ultimately, though you want to make sure your clearance holes are going to be sufficient to do just that, to clear the screws. Ultimately, because of the fact you're getting a cone-on-cone interface, that's where your control is going to occur. So if you're trying to control the alignment of the parts through this hinge, then controlling the countersink is actually a little bit more critical. The location of the countersink specifically is actually a little bit more critical than controlling the clearance holes. So that's why we took that approach. And we did say, I think during the first session, that combining them is also an acceptable approach, and certainly a very common one.
I'm with Don. I'm ready to go fishing.
Well, the hesitation, and this is where I'd need to go and speak to our real GD&T expert who sits on the committee, is that a cone is not technically a feature of size, and so controlling it with position is, I think, the gray area that we get into here within the standard. Again, I don't want to open up that can of worms too far, but for this particular application, it was the cone that seemed to be more important for location than the clearance holes themselves.
Yep. Yeah, and I mean, there's obviously not one right answer. And one could also make the case that each of those holes is a datum, and the countersink needs position to the hole. You kind of have to balance complexity with what's required, and that's why you got to look at it from a functional point of view. If you really need that level of definition, you can go that route. But sort of to Stephen's point, the assumption here was that the countersink's going to do the work of locating the fastener, and the hole is just a clearance hole. There was, I'm not sure, Jeff Spalding had made a statement, isn't this a shall in 14.5? I'm not sure what that.
I think he's referring to the statement on qualifying the datum.
Okay.
And that's where I think that, like I think the acronym GD&T appears nowhere in the standard. I don't believe, at least I think that was true some time ago. It may have changed now, but we use it commonly. I think the term qualify a datum, I'm not sure if that appears specifically in the standard, or if it's another terminology that many people commonly use the term qualify a datum. So that's what we were responding to an earlier question. But yes, the standard says that the size, location, orientation, and form of every feature has to be controlled, has to be defined.
Stephen, there's a question about Creo 7 and GD&T Advisor.
Yeah, there was a question about, and just for everyone's sake who's looking at the chat window, we're jumping back up to the one about supporting family tables. What advice can you offer? I'm actually not up to speed on the support of family tables with GD&T Advisor. I need to check with our development, the product manager with that, to see exactly what capabilities or limitations exist there. I know that I believe we used to have some limitations or some challenges with family tables that have been improved, but that's something, Mark, that I'll try to follow up with you on afterwards.
Yeah, I could add to that too. I'm kind of a self-proclaimed expert of family tables, but Mark, you can also follow up with me. 2 years ago, as part of PTC User, we ran a working group about GD or MBD in family tables and some of the challenges, and we wrote a white paper and submitted that to PTC. I think that will definitely shed some light onto what you're asking. And it's not really just specific to GD&T Advisor, but just annotations in Creo in general, and the idiosyncrasies or pains of dealing with annotations with family tables. We had some questions that were submitted last week. Do we want to, because I don't see any new ones coming in, do we want to talk about those?
That sounds good.
Okay. Yeah, so from Blair Donewald, I'm actually going to copy and paste them into the chat session so that everybody can see them. So the first one, GD&T Advisor is meant to work in conjunction with the user defining size and location of features in Creo, correct? Is there a recommended workflow then between the two softwares, i.e. set the datum structure in GD&T Advisor, and then adding size, dimensions, and tolerances in Creo, and back to GD&T Advisor to finish qualifying the remaining features? I can take that one first, and Stephen, you can
Sure.
chime in. But yeah, there's no, in fact, jumping back and forth between, turning on GD&T Advisor and annotating and then going to Creo out of the box isn't necessary. And I wouldn't recommend it, but if you can shed any more light on that, Stephen.
So I think the statement about user defining size and location of features in Creo, let me expand upon that a bit as my understanding of that. So typically when you're working on features of size that were defined in Creo, that size dimension is there and available. And so when GD&T Advisor goes to put, say, the position and other controls you want to apply to that feature of size, we'll call it holes for now, it's going to automatically use that dimension. Where sometimes we see people having challenges is if you have a feature whose size comes from some other reference, or if you have an imported geometry and there isn't a size dimension in Creo that's associated with that feature, then yes, the user now has to go and get away from the GD&T Advisor environment, go and add the appropriate annotation of size, and then come back and apply the location and orientation and form controls that are desired. And that is something that we're trying to address. So it will occur when you have a feature of size without a parametric dimension or a driven dimension of the nominal size. Again, it comes from imported geometries, using mirror as an example, using anything that the size of a feature is actually referencing some other source for that information and doesn't have an explicit dimension on. On foreign location, I presume you're talking about putting in basic dimensions, and that is correct. GD&T Advisor is very much focused on applying the GD&T, and there's only one workflow within the tool in which it's going to create basic dimensions for you. And that's when dealing with or defining datums from targets. It'll put in basic dimension between the target points that you've used in the definition. So if you're talking about using GD&T Advisor to apply GD&T and then showing that in a drawing and wanting to put into basic dimensions, today that's the left up to the user. But I would say it doesn't necessarily have to, well, depending upon what you're trying to achieve, it doesn't have to be back and forth within the GD&T Advisor environment. With the size dimensions, absolutely. Not having those sizes becomes a blocker to doing what you want to do in GD&T Advisor. Not having the basic dimensions is GD&T Advisor doesn't care. So you can do it as you're working in the tool, or you can just wait and do all that stuff later.
Honestly, I don't have I'm not 100% confident I know the answer to the next question as far as can you control which combination state they're defined in?
You can. In fact, this is actually something that we're trying to showcase more in our demos, and we've got not to plug another seminar, but there's a PTC MBD conference coming up later this month, and one of the things that and actually Action Engineering is participating in that as well. So one of the things that you'll see in there is a quick demo of GD&T Advisor working with combination states. So what the workflow is basically whatever combination state you have active at the time of creating an annotation is where the annotation will be placed. And it also will be placed in the default all. So what you can do if you have your annotation states laid out the way you'd like them, the views that you want, you can go through the process and flip from view to view to view as you add each successive control, and it's going to show up in that, or say annotation state, combination state. I think that's the right term. The combination state in Creo, it's going to show up in that as well as the default all combination state. Does that make sense?
Yeah, it does.
Okay.
Thank you.
And again, if anyone's interested in seeing that, there's going to be a short demo in the upcoming PTC MBD conference. I believe Jennifer is speaking in. The next question, is Advisor available for ISO GPS? Yes, it is. It basically, all our demos in ASME is because that's what we use, what we're more familiar with. I can speak more intelligently on the ASME standard than ISO. I know there are differences, and I know a few of them, but certainly I'm not qualified to discuss all. But what it does is, I think it's based upon the standard you select for the part. So if you go and prepare the part, and so you're going to say the ISO DIN standard instead of ASME, or I think it's ANSI, and I can't recall. But anyways, it'll start applying the ISO rules and prevent you from using profile and the flat surface as an example of the difference. So somebody posted the date of the PTC MBD conference on the 17th. Thank you.
Yeah, Jennifer is leading this session there. There's going to be a couple people talking about successful MBD implementations. So definitely look that one up. That workflow I described earlier about, the focus being on establishing the relationships, and then, relying on a software like CETOL to do the math. I'd be interested to know how many people like that workflow. I'd say like either use that workflow or like that, and how many either don't use that workflow or don't like it. I guess a lot of that depends on whether or not you have access to tolerance analysis tools. Yep.
So, one thing that what I did with this model, this was the if I zoom in here, here's the hinge that was sent out, and we got some submissions on, and I think we sent it out with the model of how this would be put into a frame and a door attached to it. So what I thought I would do, I've actually taken the submissions, entry 1 and entry 2, and I have duplicate copies of each of those hinges based upon those submissions, and just to show the difference in some analyses that were defined on this door assembly with what was submitted, with the tolerances applied and the dimensioning scheme. This is not going to be a scientific comparison of scheme A versus scheme B with the same tolerances or anything like that. I just wanted to show some of the differences that I'm seeing in these basic analyses. And kind of, there's a couple of interesting things that come up, some of which we alluded to last time. And here I have the numbers in the software to kind of back up the general statement made last time. All right, so you'll see that I've got two positions of the door, one with it closed and one with it open all the way, where it's a very simplistic representation. I just had it open as far as it would go. And in the closed position, I wanted to make sure that the bottom of the door was never going to be below the bottom of the frame. Otherwise, presumably if the frame's on the floor, we might be scraping the floor as we open the door or close the door. And to show you what that looks like, the results of all these over here, I'll talk about those in a little bit more in just a minute, but I want to show you, just kind of show what is the analysis we're talking about by doing a quick visualization of the worst case. So here's with the door closed, and with this particular results that we're visualizing here are actually the recommended call outs of the dimensioning schema and tolerances that were discussed last time. So that's the worst case clearance, a range of worst case min and max for making sure the door has clearance. And then the other thing that we looked at is the angle. So how the term that often is used in the US is plumb, how vertical the door is. And with respect to the frame, again, there was not a lot of error here. This is because one thing I should note is all of the variation of the frame and the door itself and the position of the holes in the frame of the door has been removed. So we are dealing with a perfect frame and a perfect door. We just have imperfections in the hinges to try to isolate what is the variation being caused by the variation in those hinges. Okay, so now we see some alignment errors with it closed. And then when we have it open, similarly, we have a measurement between the floor and the bottom of the frame, or excuse me, the bottom of the door and the bottom of the frame to make sure it's going to clear the floor. Same principle, but just open. And then I did another one here. I'll show you very quickly on the actual angle. So with the tolerances, and again, this is assuming that I'm opening the door until it's hitting the edge over here. With the variation of the hinge, how much variation am I getting in how much the door can open? How important is this? I don't know. It's just something to study. And maybe it'd be better to look at, some minimum width clearance of something that I need to be able to put through this door, if that's a requirement. But just a few analyses. I didn't want to get too complex with this, something that showed the door in different positions and that we could explore for the purpose of comparing different approaches to the dimensioning scheme and tolerances assigned. All right, so let's talk about the first one here. So the door above the frame. So making sure the door is not going to rub on the floor, basically. On the left-hand side, you see a couple of things. So there's the worst case. First of all, there's my limits. I said it's got to be greater than 0. I put in a maximum of 60 thousandths of clearance. That's somewhat arbitrary. And the other one, I actually took that away. I wanted to have an upper limit just to kind of make some discussion points here. I don't know why this would be, other than maybe if we were coming in and there was actually a seal or something underneath the door, we wanted to make sure that we were getting, that it was going to have some kind of compression on that seal. That might be a typical example of why you might have a maximum gap there. And then, so this is the worst case limits. We also show the statistical limits, and we show both by default. I'm going to deal mostly with statistical. I wanted to show that worst case was there. So how to interpret this graph? Well, we still have the 0 to 60 that we're trying to fall between. We have the characteristics of the distribution. These -3 thousandths and +43 thousandths, these are the limits of that distribution at the CP of 1. So plus or minus 3 sigma, right? Or that's what these limits represent. So equivalent to what many people do when they do an RSS. Okay. And we see some quality metrics here. So we're dealing with a CPK of 0.8. Obviously, we're not centered, so we might have some room for improvement from making a nominal design change to move this distribution to the right. And we've got some other characteristics here. The one I'm going to focus in on is comparing the standard deviation of all of these, because this is a measure of the width of the variation, right? So it's kind of the worst case. As you'll see in all of these, there's quite a few contributors. So I'm hesitant to discuss this as worst case, just simply because the likelihood of getting these extremes is very small. And this is not a terribly, I presume, not a terribly critical door. So we're going to deal with this statistically and talk about the differences in the various statistical analyses between the different approaches. Hopefully that's a good intro. If there are still questions on this, please don't hesitate to put them in the chat. Someone stop me and tell me that I really need to explain something that I haven't. All right. So we have, again, these are the different results with the different entries. So comparing the door, the clearance with the bottom of the door between what we had proposed, and clearly even what we had proposed needs a little bit of work, right? We're probably going to want to tweak this either by reducing the width of this or moving it to the right so that we get more of the units above our lower threshold.
Yeah, you know what, Stephen, there is one that just came in.
What's that?
So you mentioned not taking into account any deviations in the door frame and the door, but that is something the software is capable of, correct?
Oh, absolutely. Yeah. You actually have to do extra work to turn variation off.
Okay.
but I wanted to focus in just on the hinge assembly. Yeah, basically on all the controls for the door and the frame. I went in and specifically removed those variable contributors so that we were just looking at hinge issues.
Gotcha.
Or hinge variation.
Okay.
All right. So you see here that we have a CPK of 0.86 with Ryan and my proposal. Standard deviation is just between 7 and 8 thousandths, and so obviously we need to do a little bit of work here. We're going to have some units that rub, but this is kind of a starting point. Let's compare against some of the others that came in. So on entry 1 with the GD&T and the dimensioning schema and the tolerances that were applied, we see obviously more variation. All right, the standard deviation jumps to 21 thousandths. CPK is lower. So we'll come back to that in just a second. And then on the third or second entry, again, more variation than the first, but less than the second. Standard deviation of 14 thousandths, and we're going to CPK of 0.46. So let's understand very quickly. And this actually, this was not planned. I just put it in and went through the demo, and actually this was something I had mentioned as a concern in the first meeting that we had, or the webinar that we had. So let's take a look to see what's contributing. What are my top contributors to the variation? That's what you see here underneath that. So here's the results, and here are the tolerances that have the most significant impact on the width of this distribution. If I select the first one, it takes me right to that item, and it's grayed out because that's not my active assembly state. So let's do that. So it's this position of, let me spin this around, zoom in a bit. So it's the position of the slot width, I'm on hinge 1, so it's the slot width relative to AB, right? And I think that corresponds to, yeah. So this is the dimensioning schema and tolerances that we're looking at for that entry. And I mentioned during the last call that when you're to be careful about using MMC modifier when you're trying to maintain alignment, right? So what this is showing me is this position call out from that width to the datum that was used is responsible for nearly a quarter, certainly over a fifth of the 23% of the overall variation that we're seeing here. And so we see that the tolerance is 20 thousandths. It's not terribly large. But remember, I commented on the MMC modifier that it's going to add variation in ways you may not expect. To show you very quickly and visually some detailed data behind that statement, I'm going to change this to RFS. And now notice how didn't change the tolerance, just changed the material modifier. And so we'd have to obviously go look at the size to see how much bonus was getting. But notice that now we're at, 8 or more down. So that one little M made the difference between 2% contribution from this feature or 23% contribution from this feature. So no surprise that the other one is also happening as well. So just something to be mindful of when you're using M. M is really good and very focused on getting things to fit together and giving you additional tolerance to make sure things are going to fit. But if you're trying to maintain alignment through those features of size, in this case, we're using that to kind of control the vertical position of the door, it'll surprise you, right? It's going to add tolerances and add variation in ways that if you don't take it into account, don't go study it, can really turn out to be far more than what you might anticipate. All right, so that was the interesting thing on this particular one. If we go down and just show you the difference with the second entry, just look at what was driving the things there, because obviously there were some differences here as well. So the contribution, the top contributor there was the position of the clearance hole. I'm sorry, the position of the cone, which I assumed in this case, because they combined the two, I went ahead and assumed that both the countersink and the clearance hole were positioned with the same. But they use a position of 0.5. And by the way, this one was in millimeters. So it's taking that into account automatically, but just so you know that these are in inches. What we just looked at is in inches. This is in millimeters. And so this might be an area, again, there was an MMC modifier here on both of these. So this would be an area where we might want to remove that and or reduce the tolerance. Let's just look at another one real quickly. Any questions on this, what we're trying to show here, and just how, now obviously there's difference in tolerances here, but how differences in dimensioning schemes can, you really need to kind of put it into a tool and understand what that decision is driving in terms of how it's going to impact the accumulation of variation in the assembly. There was another one that was interesting as well that I wanted to, is this it? No.
Stephen, to give you some time there, maybe now's a good time. Kate had spun up a quick poll about the question I asked earlier. So Kate, if you can hear me, you can go ahead and submit that. Oh, there it is. She was already ready. Well, that's fascinating to watch the results roll in like that. Started out, everybody said no, and now we're at like 50-50. That poll, while we're ending it up here, it looks like we closed it. That's interesting because I think there's that approach to designing I've taken since I started designing, and I know a lot of people have, throughout their design career, have done the math and enjoyed doing the math. So it's just an interesting results there. Okay. Did you have anything else? Oh, go ahead, Stephen.
I was going to admit there were many times I did not enjoy doing the math. That's why, maybe doing what I do now.
Yep. I'm in your camp.
Well, it's not a matter. Everybody can do the math. It's just a matter of having the time to do it and making sure there's no mistakes in it. That's always the challenge.
Yeah, for sure. Oh, there was a question by Mark about taking the introduction to model-based definition with Creo parametric. That's definitely not going to be a waste of time. I would say typically, though, the PTC courses focus on picks and clicks. It's not going to necessarily give you the GD&T training. So that would be my recommendation. That's fine for the pick and click type of training, but I think for GD&T principles, you still need to formal GD&T training. Here's a question from Ryan Bounds. Does CETOL semantically read the PMI from the model, or is it manually entered into CETOL?
It reads it, and so as a point, let me try to get to the first one now. First, let me make this one active. So there's actually a short video that we didn't distribute, but I think we can add. It's about 5 minutes or so to the information about these webinars, showing the PMI importing. So all of these things here that you see with the green dot, these are all pieces of tolerance information that were read directly from the CAD model. And so if it's, it's one of the many benefits of semantic definition for your tolerances. Now, obviously, companies are not going to shift to doing becoming model-based enterprises and implementing MBD across the board just for tolerance analysis. There's obviously a lot of other benefits, ingesting that information directly into your CMM software, ingesting it perhaps into your CAM software. And Ryan can probably elaborate far more than the examples that I'm giving here. But it's yet another factor where if you have this information in your CAD models, it really expedites the process of understanding this over here, of getting those results and making these design decisions on how best to control things, and maybe even what geometries make sense.
Yeah, I mean, I'd maybe just add to that with maybe a little quick story before I hand it back over to Kate. I thinking back several years, probably 6 or 7 years, when I was starting at my previous employer, some MBD projects, and one of the CTOs of one of the business units there basically stated that MBD, because everybody's looking for an ROI. What's going to be the payback on this MBD, implementing this MBD stuff, which is a cultural change, right? So it's not just about the tools and the software. I mean, there's a pretty big cultural change component to that. But he basically said that 3D tolerance analysis was the justification for all of it in his brain, and it took me a while to understand that. But when you're working in, and I came from an electronics company where you're making quantities, high volume manufacturing in the billions. So, and my background was a plastics engineer, a molding engineer. If I could just get an extra 5 to 10% allowable variability in my manufacturing process, spread out across billions of individual components, that is a very significant benefit for me as a manufacturing engineer. My tooling's going to be maybe slightly cheaper. I mean, the difference of going, a couple microns can really equate to a lot of value. And then if you're making low volumes of very expensive things, like some of the people in the aerospace and defense industry, the cost of scrapping a part can be very expensive. So even in the low volumes, I think this tolerance analysis is a very big part of the equation when trying to sell model-based definition to your company. That's my off-the-cuff opinion on tolerance analysis. Do you have anything to add, Stephen, before we hand it over to Kate for closing?
I was going to just go back to one of the earlier questions on support of family table instances. That is something that is still being worked. I'm incorrect. There's work underway. I think Ted, I texted Ted during the discussion here. He said they're targeting that for 705 and of course 801 moving forward. So still some challenges there. Still not where we want it to be, but we expect to see some improvements there in the near future.
Yeah, there is one more question, and then we'll move on to the closing. Another one from Ryan Bounds. Is it possible to define a requirement like a minimum gap and ask the software to recommend changes to your tolerancing scheme to achieve your goal?
To the tolerancing schema? No, that's not supported today. So it basically uses the proposed schema and will tell you, what tolerances are necessary or needed given the current schema to achieve the objective. Now, there are ways of using the information that it shows you to identify where you have, say, inefficient dimensioning schemas for a given variation, a given analysis. So it can help you understand where to make those improvements, but it's not a button that says, change everything and make it better. We're always, that's always the goal, but that's not where we are today.
Yeah, it's a great question, but I don't think you can get away from the need to educate people on the fundamentals of GD&T. And it's, in this model-based definition world we live in, it's no longer a language for just engineers, right? We need to extend this competency and understanding beyond engineering and into operations.
And I guess to add to that real quickly, I know we're probably pushing the time limit here. To expand upon what I just said, one of the fundamentals of defining a tolerance model in CETOL is defining these things that we call joints. Think of these as Creo assembly constraints, but these joints have additional definition, and they have that logic of which one is acting as a primary, secondary, and tertiary to capture the design intent, right? And so by using and defining your analysis model, even if you don't know your dimensioning scheme, you know how you want these things to assemble. You probably have a good idea of how you want them to behave. And as things depart from perfection, which ones are going to be controlling features? Well, through that definition and the identification of primary, secondary, and tertiary joints, i.e. assembly constraints, then it starts to drive you through the process of thinking about, okay, well, the features referenced by my primary joint are the best candidates to be primary features in the datum reference frame for their respective parts. So it's a very kind of tight interweaving of logic when you start to think about how to evaluate the variation and set up your models, and then say, okay, with this, can this information help me make better decisions on the GD&T specification side? They're very tightly related. So with that, I'll be quiet and turn it, I guess, a bit back over to you, Ryan or Kate.
Yeah, I'm going to turn my camera off. Well, there was one quick question. Can CETOL simulate kinematics? And we can follow up later on that.
Yeah, send me more detail. It's not a kinematic. We use kinematic methods to do the analysis, but it's not a kinematic tool. It's not. We're looking at kinematics over a very small range of motion, not something broader. There's some data that you can get out of it. So if you let me know, send me more information about what you're looking for, I can be more definitive in my answer.
Okay. All right. So I'll hand it over to you, Kate. Thanks, everyone. Appreciate the opportunity to have this discussion in front of you all again.